You're probably familiar with the concept of tilings. In fact, you're probably only a room away from one. Tilings can be found everywhere, and they include such famous patterns like squares, rectangles, funky rectangles, squares with little squares, long rectangles, and diamonds. But what if you don't like quadrilaterals? Are you out of luck in regard to tiling? Well, no, not even close, because in the world of geometry, tilings have much more variation than these examples would imply. Instead of the practical limitations of reality, we're limited only by our own creativity. Tilings are one of my favorite examples of mathematical beauty, and in this video, we'll look at all the different examples that make that the case. These include regular tilings, semiregular tilings, Laves tilings, Monohedral tilings, pentagonal tilings, Polyominoes, making a tiling from any shape, wallpaper groups, Aperiodic tilings, and more. We'll get to all of those in this video, but first we have to start with the basics. A tiling, also known as a tessellation, is simply a way to cover a two-dimensional surface with shapes without any gaps and without overlapping. For the purposes of this video, that surface will be the flat plane, and tiles must have a finite continuous interior. Having a repeated pattern is not a requirement, but most tilings do have some amount of regularity. This regularity can come in several forms, and this is key to how we categorize tilings. In this video, we will go from most to least regular, which also corresponds with simplest to most complex. With that out of the way, let's get into some tilings. First are the regular tilings, which have two main requirements. Every tile must be a regular polygon, and every tile must be the same shape. Combining these, it's pretty simple to form regular tilings. Just pick a regular polygon, and then repeatedly attach it to copies of itself. With squares, you could fit 4 around a corner, which results in this, the regular square tiling. This is by far the most important tiling since it's the basis of our coordinate system, which relates to our intuition for all tilings. With triangles, you could fit 6 around a corner and you get this, the regular triangular tiling. Half of the triangles are upside down, but they're still the same shape. And then with hexagons, you can fit 3 around a corner and you get the regular hexagonal tiling. Unlike the last two, it can't be easily scaled up or down, but what it lacks in recursion, it makes up for it in efficiency, because it has the best ratio of border length to tile area of any tiling, which is important if you're building cell walls. Due to this, it's one of the few tilings discovered by a different species before humans, although its history can go even further back. Now something interesting happens with pentagons. With 3 around a corner, you get a gap, but it's too small to fit a 4th one. Due to this, pentagons don't form a regular tiling, and a similar thing also applies with anything past hexagons. So it seems that the 3 aforementioned ones are the only regular tilings. And this is true, but they're actually not the only ones that meet the requirements. That's because there's also a subtle third requirement, the edge-to-edge property. Basically, you can't have multiple shapes along an edge without the intersections becoming new corners, thereby dividing the edge. Without the edge-to-edge rule, you could do things like shifting over some of the rows. And in fact, if you allow differently sized tiles of the same shape, then it would allow things like the Pythagorean tiling, this triangular version, and the famous squared square. I could even see an argument be made that pentagons work if you allow things to go fractal. None of these are regular tilings due to not being edge to edge, but it's not just an arbitrary restriction. The technical definition of a regular tiling is that its symmetry group acts transitively on its flags. Basically, you can map any tile onto any other without changing the tiling, and same for edges and corners. Even with the highly symmetrical brick pattern, you can't map this edge onto this one because they're fundamentally different. Anyway, now it's time for the second main group of tilings, the semi-regular tilings. They follow the same rules as the regular tilings with one small change. Instead of requiring every tile to be identical, they only require every corner to be identical. So basically, you can mix and match regular polygons as long as they meet up the same way every time. Now you could find them by just trying out different corners and seeing which ones work, but there's an alternative method that I think is more fun. Specifically, we can make use of the existing symmetries of the regular tilings and make modifications to them. The main important operation is truncation. Basically, you take a tiling and add more tiles in the corners. The shape you add will depend on how many shapes meet at each corner. For example, the hexagonal tiling has 3 shapes per corner, so the new shape will be triangles. When you add them, the original hexagons double in edge count and become dodecagons. And if you get the proportions exactly right, they become regular dodecagons satisfying their requirements. Therefore, the truncated hexagonal tiling is our first semi-regular tiling. There's also an operation known as rectification. It's just like truncation, except you make the new tiles big enough so that the original edges go away. So if you truncate the hexagonal tiling, the hexagons turn to dodecagons, but if you rectify it, they turn back to hexagons, now with triangles in between. What results is another semi-regular tiling known as the trihexagonal tiling. So now let's see if we can truncate and rectify the other two regular tilings to get 4 more semi-regular tilings. The truncated square tiling is composed of octagons and squares. It's actually pretty popular in real life with varying proportions. But if you try to rectify the square tiling, the new tiles are squares, but the octagons turn back to squares as well, and you just get the square tiling again. Now onto the triangular tiling. If you truncate it, the new tiles are hexagons, but the old triangles turn to hexagons themselves, and you're left with the hexagonal tiling. Finally, if you rectify the triangular tiling, you actually end up with the trihexagonal tiling, so there's not as many as you might think. But we're not done yet. The trihexagonal tiling is unique because it shares a property with the regular tilings. It only has one type of edge, the triangle to hexagon edge. Due to this, further truncation or rectification will only result in one type of corner, theoretically generating 2 more semi-regular tilings. Now technically, the new tiles created in this process are only rectangles, not squares, but we can rebuild the same basic layout with squares to get 2 more semi-regular tilings. The rectified trihexagonal tiling, also known as the rhombi trihexagonal tiling, is composed of triangles, hexagons, and squares. It has a really interesting variation which can be constructed by the overlapping edges of expanding circles. And then there's the truncated trihexagonal tiling. It's made of dodecagons, hexagons, and squares. This one is unique because half the corners have the shapes in this order going clockwise and half have it going anti-clockwise. They're still counted as the same type for semi-regularity, but we can use this discrepancy to do something called half truncation, where we only truncate half the corners. Similar to before, we have to rebuild the structure with regular triangles, but in doing so, we get another semi-regular tiling. It's called the snub trihexagonal tiling and has 2 different versions, which are mirror images of each other. So half truncation is pretty cool, but can it be used on any other tilings? Well, if you apply 3 different colors to the hexagonal tiling, you once again get 2 types of corners. Half truncation in this case only results in the triangular tiling, but we can do a similar thing on the truncated square tiling. That results in a very unique tiling called the snub square tiling. I really like this one because it reminds me of those folding cubes you can make out of paper. Anyway, these 7 are all the semi-regular tilings you can make with the operations of truncation and rectification. But are they the only semi-regular tilings? To be sure, we'll have to systematically go through all possible corners and see which ones can form semi-regular tilings. If you want to see the process in detail, I showed off a similar thing in the almost platonic solids, but long story short, we end up with 21 valid corners. 10 of them are things we've seen before, either regular or semi-regular, and another 10 can't form semi-regular tilings because if you try to fill them in with that corner, they necessitate the presence of other corner types. But that still leaves one corner, known as 33344, featuring 2 adjacent squares and 3 triangles. Miraculously, you can actually tile the plane with it, and it forms this stripe pattern. It's called the elongated triangular tiling, and is the only non-Wythofian semi-regular tiling. With that, we've discovered all 8 semi-regular tilings, and they make up a pretty cool collection. If you're an existing fan of the channel, then looking at these might invoke a sense of familiarity. That's because semi-regular tilings are the tiling equivalent of the Archimedean solids. But if these are the Archimedeans, then where are the Catalans? Well, their equivalents actually have a special name. They're called the Laves tilings and are the next main category. To find them, we need to introduce the idea of duality. Every tiling has a dual tiling, which can be found by following the following process. At the center of each tile, make a point. Then if 2 tiles border each other, you connect their corresponding points. You repeat for all connections for all tiles, after which you can ignore the original tiling. The newly created lines function as edges, and they subdivide the plane into a new tiling, specifically the dual of whatever you started with. As you can see, the dual of the hexagonal tiling is the triangular tiling. Likewise, the dual of the triangular tiling is the hexagonal tiling, since it's a 2-way operation. As for the square tiling, if you take the dual, you actually just get the square tiling again, making it self-dual. But what about the semi-regular tilings? Well, their duals are called the Laves tilings, and they're pretty interesting. Now, we could just go through the semi-regular tilings one by one and take the duals, but once again, there's a more fun way. Instead of truncating and then taking the dual, you could take the dual and then execute the dual operation of truncation. But what is the dual operation of truncation? Well, instead of adding a new tile at each corner, you add a new corner at each tile, then connect to the original corners to subdivide the tiles. Applying this to the triangular tiling is how we get our first Laves tiling, the triacus triangular tiling, which is composed of obtuse isosceles triangles. From there, you can also remove the edges from the original tiling in the dual form of rectification. In this case, it results in something called the rhombile tiling, composed of 60 and 120 degree rhombi. This tiling is pretty famous for representing a three-dimensional grid of cubes from an isometric perspective, which is made more clear by coloring the different sides. And in fact, you can even rotate sections of it to build your own world. But enough about the rhombile tiling. What happens if we try this on the other tilings? Subdividing squares results in the tetrachus square tiling, composed of isosceles right triangles. This one might be familiar if you've done origami that involves grids of diagonals. But removing the original edges just gives you more squares. As for subdividing the hexagonal tiling, it just gives you the triangular tiling, and if you remove the original edges, you get the rhombile tiling again. However, the rhombi can themselves be subdivided, resulting in this. It's made of everyone's favorite, the 30-60-90 triangle. If you remove the original edges, you get the deltoidal trihexagonal tiling, which is made of kites. It can alternatively be constructed by overlaying the dual triangular and hexagonal tilings. But let's get back to those 30-60-90 triangles. This is actually our first time seeing a chiral shape, which means it doesn't equal its mirror image. The different versions are called chiralities, and the tiling contains an equal amount of both. If we only subdivide one type, then we can get rid of the old lines to get another Laves tiling. This is the floret pentagonal tiling, and is our first time seeing pentagons in a tiling. They may not be regular, but that allows them to form these beautiful flower shapes. Now, if we go back to the other Laves tilings, none of them have chiral tiles, but on the tetrachus square tiling, we can use color to subdivide half the triangles, resulting in this. It's named the chiro tiling because it was apparently popular there long ago. It would have to be one of my favorites because it's pretty much the closest thing to the non-existent regular pentagonal tiling. The final Laves tiling is the dual of the non-Mythophian elongated triangular tiling and is called the prismatic pentagonal tiling. With that, we have all 8 Laves tilings. And to be honest, I like them a bit better than the semi-regular ones. Something about the shapes they use is just aesthetically appealing to me. Speaking of which, these specific shapes are called Pentagons. Each one can form a tiling on its own, as seen by the Laves tilings, but there's more to them than that. Since most of them have angles that are multiples of a 12th of a circle, it means they all fit together really nicely. This lets us do something called fractalization. Basically, if you can build a Pentagon out of Pentagons, then you could take that Pentagon's corresponding Laves tiling and replace instances of said Pentagon with the meta Pentagon to get some pretty cool patterns. As an example, I came up with this fractalization of the triacus triangular Pentagon, and I really like how the resulting tiling ended up. And of course, the shapes you use for fractalization don't have to be Pentagons. Here's one I made with some irregular quadrilaterals and pentagons. From there, you can even get truncation involved. Another way to make new tilings is just filling in shapes one by one. The aforementioned Pentagons work great for this due to their angles. On a similar note are the Giri tiles, whose angles are multiples of a 10th of a circle. There are 5 main tiles, and each one is given a strapwork pattern. If you look at these lines rather than tile edges, you can get these cool patterns, which are a staple of Islamic architecture. And although not officially Giri tiles, multiples of 36 degrees are found in the golden triangle and golden gnomon, which also heavily feature my favorite number, the golden ratio, and are found in the fractalization of a pentagon. And of course, you could do the same thing with multiples of 45 degrees or an 1/8 of a circle to get these really square-based patterns. Now, with so many tiles at your disposal, there's pretty much no limit to what you can make, since you can always introduce a tile for any scenario. These tilings are beautiful, but sometimes it's more fun when you give yourself restrictions and work around them. So it's time for our next main category of tilings, the monohedral tilings. Monohedral tilings are defined by only having one shape. More specifically, every tile is congruent. That means you can rotate and flip that shape, but you can't scale it up or down. Now, do reflections really count as the same shape? I have mixed feelings on it, and there are certainly contexts in which distinguishing chiralities is important, but the standard definition of monohedrality allows reflections, so that's what we'll stick with. If a shape can form a monohedral tiling, it's said that the shape tiles the plane, and the shape is known as a monotile. As we've seen, all the Laves tilings are monohedral, meaning their corresponding shapes can all tile the plane. But what other shapes can tile the plane? Your first thought might be rectangles. They can tile the plane in several unique patterns. Stack bond is essentially the square tiling just stretched out. Running bond has half the rows offset by half a brick, and it has more structural integrity. Wood strip is similar, but the offset is smaller. It's commonly done with long rectangles. Basket weave combines rectangles into squares and has half the squares rotated to achieve this woven look. And then there's herringbone. Essentially, you take a rectangle and repeatedly attach more diagonally along part of the long edge to get these ribbons. From there, you can flip the ribbon and attach them along the zigzags in what I'm going to call the ribbon technique. Herringbone is very common in real life, and once you know about it, you'll start to notice it everywhere. It's most often seen with 1x2s, but you can actually use any aspect ratio, even irrational ones. But enough about rectangles, what about rhombi? Well, they're just squares stretched along the diagonal, so they easily tile the plane as well. In fact, any parallelogram can tile the plane, since these tilings are essentially matrix transformations of the coordinate grid. But it's not just parallelograms. Actually, any quadrilateral can tile the plane, even concave ones. To see why, you can assign a unique color to each edge and follow the rule of only attaching edges of the same color. Surrounding one tile must be 4 rotated copies of itself. Since the interior angles on a quadrilateral always add up to 360, the gap will be the exact size to fit the 4th corner, at which point you can repeat the process. And if you're curious, here's what it looks like with concave quadrilaterals. As for triangles, since triangles can always form parallelograms, and all parallelograms tile the plane, it means all triangles tile the plane very easily. But of course, don't go thinking all triangular monohedral tilings are like this. We've already seen some variety in the form of the Laves tilings, but there's more than just that. One of my favorites looks like this, and it involves the 45-45-90 triangle. Combining them in different ways can give you squares of different sizes, and you can use these to simulate the Pythagorean tiling. The same thing about variety applies to quadrilaterals. After all, parallelograms can do herringbone as well, and with so many ways to subdivide, the possibilities are endless. So yeah, triangles always tile the plane, and quadrilaterals always tile the plane. But pentagons are where things get complicated, since not all pentagons tile the plane. We know of one that definitely doesn't, but 3 that do. So are there any more? The answer is yes. In fact, there are so many that pentagonal tilings get their own small section. There are at least 32 types of pentagons that tile the plane, 28 of which are infinite families. The other 4 I'm going to call fixed pentagons. 2 of them are convex and 2 are concave. As for the infinite families, 4 only allow for convex pentagons, 15 only allow for concave pentagons, and 9 include both types. The 15 types that include convex pentagons are very well documented. They each have specific numbers 1 to 15, and it's proven that if a convex pentagon tiles the plane, it must be of one of these types. Concave pentagons, on the other hand, are much less popular. I'm not entirely sure why, but I think they're just harder to work with. We don't know how many types there are, and the only categorization of them I found was on this website by Jaap Surface. He made a program to systematically find such tilings and visualize them, along with hundreds of other tilings, which is not only amazing, but also free to download, so please do check out his website for more information on them. Anyway, 32 types is too many to cover each one in depth, so I'll just give some highlights. Type 1 is by far the simplest, and only requires there are 2 adjacent angles that add to 180. Combining 2 pentagons along the relevant edge gives you a hexagon, and from there you can easily use the ribbon technique. Concave type 1 is very similar, but the 2 angles add to 360. Connecting 2 copies along this in-between edge also forms a hexagon, albeit a weird one, but you could still use it for the ribbon technique. Type 2 is like type 1, but the angles are not adjacent, and it requires 2 edges to be the same length. To connect them sustainably, you have to get the mirror image involved, but doing so allows you to form ribbons. Just like before, type 2 also has a concave equivalent. The next 3 are all similarly simple, because it's very easy to subdivide a triangle, square, or hexagon into 3, 4, or 6 pentagons respectively. You can also split a hexagon into 3 pentagons for type 3. Type 4 requires 2 non-adjacent right angles, each surrounded by equal sides. With 4 around a corner, you get a unit that can tile the plane like a square. The resulting tiling will look Cairo-esque because the Cairo tiling is of type 4. Then type 5 is pretty much the same thing, but the angles are 60 and 120, and it corresponds to the floret pentagonal tiling. Concave type 11 is interesting because the angles are all fixed, and the only variation is on the side length proportions. Concave type 9 is pretty cool because 2 pentagons combine to form a crescent shape, and the resulting tiling is wavy. And then types 7 to 13 minus 10 are all variations on the same idea. Combine 4 pentagons into a unit that tiles the plane in a herringbone fashion. Also, I want to give a shout out to type 15. It's one of the 4 fixed types, and interestingly, all the angles are multiples of 15 degrees. The same is true of concave type 8. Now, each of the 32 types comes with an algorithm to tile the plane. After all, that's how we prove they're even able to do so. But you don't always have to use them. Sometimes a pentagon can tile the plane in a unique manner outside the main algorithms, but it doesn't count as a new type because it's already one of the existing types, usually type 1. I'm a big fan of this one, which looks like a bunch of overlapping squares. There's also this concave type 1 pentagon, which can tile the plane in a variety of ways, one of which contains these spiral regular dodecagons. Speaking of spirals, there's even the Hirschhorn tiling, which spirals out forever. But again, the tiles are of type 1. It's honestly amazing how much can be done with just pentagons, but for now, it's time to move on. Hexagons surprisingly only have 3 convex types that tile the plane. Type 1 requires 2 opposite sides that are the same length and parallel. You can repeatedly connect these sides to get ribbons for the ribbon technique, but instead of flipping the ribbons, you actually have to rotate them. Keep this in mind, it'll be important later. Type 2 has a few edge and corner requirements. Similar to some from earlier, you combine 2 of them to get a decagon unit for the herringbone process. And then type 3 has 3 non-adjacent 120-degree angles, each surrounded by equal sides, and the tiling is pretty straightforward. As for concave hexagons, well, there's probably even more variety than the pentagons, but finding tilings is much more tricky and time-consuming, and they're mostly variations on ideas we've already seen. With that, we actually have all convex monotiles. All triangles, all quadrilaterals, 15 types of pentagons, and 3 types of hexagons are the only possible convex shapes that tile the plane. But there's still plenty of concave monotiles past hexagons. Here's one made of arrow-shaped heptagons. Here's one with almost regular octagons. And there's even the Voderberg tiling, made of the strange-looking nonagon/enneagon, which spirals out forever. But as we add more sides, the tiles start to lose their identity as polygons. What I mean by that is the number of sides is far from the most relevant thing about this shape. So instead of looking at every n-sided polygon, it now makes more sense to look at specific types of shapes, disregarding edge count. So for the next main category, instead of polygons, we're going to look at polyominoes. The name is a pun. Since a domino is basically 2 squares put together, you can form a mathematical folk etymology by saying it's di meaning 2 plus omino meaning square. This implies the existence of other polyominoes. For example, pentominoes would consist of 5 squares. We're going to go through the types in order, starting with monominoes, aka squares. There's not much more to say about them except for the fact that we usually choose to keep polyomino tilings grid aligned. Next up are dominoes, which again were already covered since they're 1x2 rectangles. However, contextualizing them as dominoes reminds me of a cool tiling puzzle called the mutilated chessboard problem. The premise is that you cut off 2 opposite corners on a chessboard, and the goal is to either tile the area with dominoes or prove it's impossible. Triominoes are slightly more interesting since there are actually multiple types. There's the 1x3 rectangle and the hexagonal L. Both of them tile the plane very easily, and you can also mix and match. Tetraominoes are the first type to include chiral polyominoes. How many there are depends on whether you count different chiralities separately, so it said there are 5 free tetraominoes and 7 one-sided tetraominoes. With tetraominoes specifically, the one-sided interpretation is more common. Now, it's a well-known fact you could tile a 10x18 grid using all 7 in roughly equal amounts. But you can also do monohedral tilings. The easiest way is usually to form rectangles, but you don't have to. In fact, 2 of the shapes are unable to form rectangles, so we have to get a bit more creative. Next are the pentominoes, which might be my favorite of all polyominoes. There are 18 one-sided pentominoes, but this time the free interpretation is more common, in which case there are 12. When you're allowed rotations and flips, there's a really cool puzzle of using one of each type to tile a rectangle. There are actually 4 possible aspect ratios, and you can also do an 8x8 square minus the center. In fact, I like the pentomino puzzle so much that I jigsawed them out of wood, which is by far the best way to experience the puzzle. Sometimes you get it first try, but sometimes it's really difficult to put the pieces together. Now, what about monohedral tilings? Well, all 12 types do indeed tile the plane, but some of these tilings are pretty tricky to find. Clearly, testing each one individually is not sustainable in the long term, especially considering how fast the number of level n polyominoes is growing. As it turns out, there is a simple way to tell if a shape tiles the plane, called the Conway criterion. A shape satisfies the Conway criterion if it's possible to subdivide it into 6 segments with the following 2 properties. 1, there's a pair of opposite segments where one is a translated copy of the other, and 2, each of the remaining segments is rotationally symmetrical by 180 degrees. It's worth noting these segments can also be empty, you just need at least 3. Using the duplicated segment, you'll be able to form ribbons, and since each remaining side connects to itself, you'll always be able to connect rotated ribbons. Therefore, if a shape satisfies the Conway criterion, then it's guaranteed to tile the plane by virtue of this algorithm. So with that out of the way, let's take a look at the 35 free hexominoes. As you can see, some of them are quite complicated. We'll look at this one for example. This zigzag is centrosymmetric, as is this straight line. The next section is identical on both corners, after which all that remains is another centrosymmetric zigzag and straight section. This means the hexomino satisfies the Conway criterion, and therefore tiles the plane. Doing this with all the hexominoes is pretty simple, and we can see all of them satisfy the Conway criterion, and therefore tile the plane. With some of them, we don't even need to invoke the translated section, and it's a fun puzzle to see how efficient you can be. Next up are the 108 heptominoes. Actually, there are only 7 that don't satisfy the Conway criterion. 3 of these are able to combine with themselves to form shapes that do, but the other 4 can't do so, and in fact they can't tile the plane in any other way either. The same thing applies to the 369 octominoes. 320 satisfy the Conway criterion, 23 can merge into shapes that do, and the remaining 26 are unable to tile the plane. It's not until non-ominoes that we get one that tiles the plane without the Conway criterion. But even still, it satisfies a similar criterion with 3 pairs of duplicated segments. Another non-omino tiles the plane by merging 8 of itself into such a shape, but the remaining 1,283 either satisfy the Conway criterion, form shapes that do, or don't tile the plane. So yeah, the Conway criterion is pretty powerful, but we haven't even gotten to its coolest application yet. So far, we've taken existing shapes and checked whether or not they meet the requirements to form a tiling. But what you can do instead is design your shapes with the Conway criterion in mind. Using this technique, you can convert any shape into a monotile without even sacrificing too much. Well, not all of them can be winners, but sometimes you can get remarkably close. Take for example, Sulawesi, in my opinion the funniest shaped island, and yet I made a tiling out of it using the Conway criterion. The trick is to find peninsulas next to gulfs and combine them into a centrosymmetric segment. I also made tilings of Mozambique, Croatia, and Maryland. The Conway criterion was first formalized by John Conway in the 70s, but it was undoubtedly known earlier. For example, just look at this seahorse piece by M.C. Escher, which I think is really beautiful. In addition to art, there are also potential applications like making a cookie cutter without wasted space. After a while of using the Conway criterion, you'll notice the resulting tilings all look pretty similar. They basically consist of 2 rotated tiles stuck together into a rotationally symmetric shape, which is then translated across the infinite plane in 2 linearly independent directions. In fact, looking back, a lot of tilings have looked similar to each other, featuring things like hexagonal patterns or the herringbone strategy. So why is this the case? Well, the answer all comes down to symmetries. If an object has symmetry, it means there's some operation you can apply that leaves it looking the same before and after. In 2 dimensions, there are 4 main types of symmetry. With translational symmetry, you could shift the entire tiling over in some direction by a certain distance. We could describe translations using vectors, aka arrows. With rotational symmetry, you can rotate the entire tiling around a center point. Some centers only allow 180-degree rotations, while some offer more options like multiples of 90 degrees. We'll represent the centers with different shapes depending on the smallest rotation. With reflectional symmetry, you can flip the tiling across some straight line. Pretty simple. We'll represent them with solid lines. And finally, there are glide reflections, where you have to flip across a line and then shift the tiling along that line to return it to how it was. We'll use dotted lines for them. But translational symmetry is the most important type. Tilings with translational symmetry are known as periodic. The vast majority of tilings we've covered are not just periodic, but double periodic, meaning they have translations in multiple directions. Double periodic tilings can be further categorized by which of the other symmetry types they have. In total, there are 17 possibilities known as wallpaper groups. To determine what wallpaper group a tiling is, we use something called a fundamental region or unit. Basically, you use two linearly independent translation vectors as edges on a parallelogram, and this is your fundamental unit. Due to the translational symmetries, you only need a single one to describe the tiling, making it a fundamental unit. Now technically you can place this fundamental unit at any offset, but we usually make sure it lines up with the existing reflections and rotations. Speaking of which, the next step is to identify all the reflections, glide reflections, and rotations. Since these symmetries repeat in the same way the tiles do, you can represent them in their entirety on a single fundamental unit. This is called the cell structure, and if tilings have the same cell structure, they're in the same wallpaper group. Actually, they don't have to be exactly the same. The parallelograms can be different, all that matters is where the symmetries are in relation to the parallelogram. With that out of the way, let's get into the 17 groups. Now, there is an official way to classify and name them, but I came up with more memorable names for each. First is wallpaper group R. I named it as such because it's just like the letter R. It has no reflections or rotations, only translations, making it the most basic wallpaper group. Next is wallpaper group S, named for the same reason. Its only additional symmetry is 180-degree rotations. This is the wallpaper group of most Conway criterion constructions. And then the spiral wallpaper group is basically the same thing, but with 90-degree rotations. The most famous example is probably the Pythagorean tiling. The traditional wallpaper group has diagonal reflections in a single direction, which also necessitates the existence of glide reflections in between. I named it as such because it's pretty popular among literal wallpaper patterns. And then the running bond wallpaper group has diagonal reflections in both directions, which necessitates the existence of 180-degree rotations. It's named after its most famous example. Wallpaper group A has axis-aligned reflections in a single direction, and is named after the letter A. Don't get it confused with the traditional wallpaper group. This time the reflections are aligned with the grid, not diagonal. The rectangular wallpaper group has axis-aligned reflections in both directions, as well as 180-degree rotations. Examples include rectangles in stack bond. Again, don't get it mixed up with running bond. Adding diagonals upgrades these to 90 degrees for the square wallpaper group, named after the square tiling. It has pretty much all the symmetries possible in this configuration. Now it's time for glide reflections. With one axis-aligned set of them, you get the cascade wallpaper group. I named it that because if you look closely, there is a clear direction, but to follow it, you swap between mirror images. The zigzag wallpaper group has reflections going one way and glide reflections going the perpendicular way, as well as 180-degree rotations, but offset from the reflections. An infinite zigzag pattern is a good example, as well as patterns made with chevrons. The herringbone wallpaper group has glide reflections both horizontal and vertical, and 180-degree rotations in the center of each quadrant. Alternatively, you can place the fundamental unit with them in the corners, in which case the glide reflections are offset. Its most notable example is the namesake herringbone, but there are others too. Then the crosshatch wallpaper group is, in my opinion, the most complicated one. It has those same axis-aligned glide reflections as herringbone, in addition to diagonal reflections, and the rotations are upgraded to 90 degrees. You have several choices of how to place the fundamental unit. The basket weave is a good example, but it's also the wallpaper group of the snub square and Cairo tilings. The last 5 wallpaper groups are unique because they don't work with squares. Instead, the fundamental unit has to be a 60 and 120 degree rhombus. This allows more rotation options, plus the ability to have 3 reflections, not just 1, 2, or 4. First among these, the tri-twist wallpaper group has no reflections or glide reflections, only 120-degree rotation. A great example of it is hexagonal tiling type 3. The hex twist wallpaper group is similar, but some of the rotations are upgraded to 60 degrees, with 180s in between. Examples include the floret pentagonal tiling. The basement wallpaper group has 3 reflections and glide reflection directions, all of which are aligned with the translations. I named it after this tiling, whose name I don't know, if it even has one. The chromatic wallpaper group is very similar, but the reflections aren't aligned with the translations. The easiest way to achieve it is by coloring the triangular tiling with 2 different colors, which makes some reflections no longer work. But you don't need colors to make a tiling of this group. Finally, the hexagonal wallpaper group has all of those previous reflection directions and 60-degree rotations. It includes the regular hexagonal and triangular tilings, as well as half the Laves tilings. And this chart shows how you can identify the different groups. With that, we finally have all 17 wallpaper groups. Knowing about them not only recontextualizes every tiling you see, but also helps you design new ones. But remember, they only apply to double periodic tilings. Single periodic tilings, those with only one translation dimension, can be similarly categorized into the 7 freeze groups, which mainly apply to other infinite patterns, but can also apply to tilings. But what if you want to defy translational symmetry entirely? Well, that's where aperiodic tilings come in. They're defined as tilings without any translations, and they're really easy to make. For example, take 1x2 stack bond and twist one square of rectangles. This is technically an aperiodic tiling because no matter where you translate it, there's nowhere for the vertical tiles to go. But this is extremely boring. What else can we do? Well, another aperiodic technique is pure randomness. The Voronoi tiling is a technique where you place a few points across a surface and color in the remaining area based on which point you're closest to. Alternatively, you can think of tiles expanding outwards from these points, claiming unclaimed area. The resulting tiles have about as much regularity as the points you started with, so it's easy to get an infinite random pattern, which obviously won't be periodic. Or if triangles are more your thing, then there's the Delaunay triangulation, which uses the points as corners and is actually the dual of the Voronoi tiling. But at this point we're getting away from tilings. The main appeal of tilings, to many people including myself, is their patterns and irregularities. So ideally, we want to find tilings with regularity, but not periodicity, that aren't extremely boring. The main form of regularity is the monohedral property, and there do exist plenty of monohedral aperiodic tilings. For example, the spiral Hirschhorn and Voderberg tilings. There's also the pinwheel tiling, which looks random at first, but has a really cool construction. You start with a 1x2 right triangle and subdivide into 5 copies of itself. You can then subdivide each of those in 5, and so on and so forth, for another really cool aperiodic tiling. However, in all 3 cases, the tiles can easily tile the plane periodically. That raises the question, are there any shapes that tile the plane but only aperiodically? Such a shape is known as an aperiodic monotile, and finding one is considered the holy grail of tiling. To turn it into a problem we can actually make progress on, the question is rephrased a bit. Is it possible to construct a set of tiles that tiles the plane but only aperiodically, and how small can you get that set down to? The first progress on this front came in the form of Wong tiles. These are essentially squares where each side is a different color. When connecting them, you're only allowed to connect each color to itself, and you can't rotate or flip the tiles. Since the tiling relies on additional matching rules outside of what's physically possible, they aren't really tiles in the traditional sense. But we can remedy this by simply converting colors into shapes that connect in equivalent ways. This still doesn't enforce the no rotations or reflections rule, but I came up with an algorithm to do that as well. Now, the set I've been showing is the smallest possible aperiodic Wong tile set with only 11, and was discovered in 2015. But the first aperiodic Wong tile set was found in 1966 and had 20,426 tiles. The number was gradually lowered, but in the meantime, other types of aperiodic sets were found. For example, the 6 Robinson tiles are very similar. They don't have any matching rules, but they do have an additional thing to pay attention to in the form of this corner square, only found on one of the tiles. Then there's the famous Penrose tiling. Its formulation is heavily tied to pentagons. Throughout this video, we've seen how pentagons don't work very well in the realm of regular and semi-regular tilings. Even the monohedral pentagonal tilings kind of have more to do with other shapes due to the wallpaper groups. So how can we make a tiling that is inherently pentagonal? The trick is fractalization. You can replace a regular pentagon with 6 copies of itself with only a few gaps. If you repeat the process on the smaller ones, you get narrow rhombic internal gaps. If you go down another level, they grow spikes, but now you can fit in another pentagon, resulting in 2 new shapes, the star and the boat. And at this point, we can actually ignore external gaps by simply zooming in. Anyway, if you go down another level, the stars and boats grow spikes also, but you can add more pentagons to get the same gap shapes again. No matter how many levels you go down, the only internal gap shapes are the diamond, boat, and star. So, you can form a tiling out of these 3 shapes plus pentagons. This is the Penrose P1 tiling. Of course, the 4 shapes on their own don't enforce aperiodicity, but you can fix this with a few simple matching rules. Unfortunately, this requires 6 tiles, which isn't any less than the Robinson tiles, but Penrose quickly noticed something interesting. If you remove these cyan pentagons, the gaps can be absorbed into other shapes, and now you only have 5 tiles. You can actually repeat this process to get all the way down to only 2. This is the Penrose P2 tiling and is composed of kites and darts. The matching rule is pretty simple. You just assign the corners 2 different types and only allow 1 type per intersection. Alternatively, you can give each side a letter and then be like DNA and only connect A to T and C to G. The most popular form of the Penrose tiling is P3 with 2 different rhombi. They use the same DNA style matching rules. But remember, in all 3 forms, the shapes themselves tile periodically as well, so for it to technically count as an aperiodic set, you have to incorporate the matching rules in the geometry itself. Another interesting way to express them is with colorful lines which must connect. With the circles like this, it's actually very reminiscent of quasicrystals, which are aperiodic crystal structures that form under very specific circumstances, such that the atoms arrange themselves according to 5-way rotational symmetry, for example. Anyway, for about 50 years, the Penrose tiling stood as the world record, the smallest aperiodic tile set. But in 2022, David Smith came up with this shape. It's known as the hat, and is made of 8 of those kites from the deltoidal trihexagonal tiling. He noticed it tiled the plane in a really weird way, and that's because he'd actually discovered the long-awaited aperiodic monotile. He teamed up with experts to publish a proof of its aperiodicity a few months later, and in the process also made a version called the Spectre that tiles without needing its mirror image. But how do you go about proving a tiling is aperiodic? Well, it all comes down to recursion. We'll look at the pinwheel tiling, for example. Due to its formulation, every triangle is part of exactly one level 2 triangle. Each one of those is part of exactly one level 3 triangle, and so on, in a hierarchical structure. So no matter how big a translation you do, there's always a triangle bigger than the translation, which means after the translation, it will overlap where it was before. If there's translational symmetry, the tiling must remain unchanged, meaning both forms are present simultaneously in the original. But for that to be true, triangles within the overlap would be part of 2 level 3 triangles, which contradicts the hierarchical structure. Therefore, the tiling can't possibly have translational symmetry. A similar thing applies with the Robinson tiles. If we mark the tiles with colorful lines, we can see a pattern. At the center of each pink square is a corner of a larger pink square, and so on. There's also the hierarchical nature of the Penrose tiling, since that's how we originally formulated it. Proving that the matching rules necessarily result in said hierarchical structure is much more tricky, but still possible. As for the aperiodic monotile, if you look closely, you'll notice some structural patterns. If you convert these structures into 4 different types of tiles, then its hierarchical structure is revealed. The aperiodic monotile really shows why I like tiling so much. Its creator, David Smith, isn't even a professional mathematician, but rather a geometry enthusiast, and yet he made the biggest mathematical breakthrough of the year by simply messing around with shapes. It shows how tilings are not only fun to develop and beautiful to look at, but they also have potential to reveal deep mathematical truths about our universe. In other words, I love tiles. If you've watched this far, clearly you love tiles as well, in which case I have a somewhat exciting announcement, which is that I made a Discord server for fans of my content. I wanted to become a fun place to hang out and talk about math and science or other unrelated stuff. I'll have a link in the pinned comment, so feel free to join. With that out of the way, we've reached the end of the video. This kind of accidentally became my longest video ever, and I really put in the extra effort to make it truly a masterpiece, so make sure to like and subscribe, as well as comment your favorite tiling. Thank you for watching, and I'll see you next time. Bye!